Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which I'll show you how to multiply two matrices together. So there's a number of points we have to make about matrix multiplication. So the first point I want to make is that if you have two matrices, it is not always possible to multiply them together. They have to have compatible orders. So remember, the order of a matrix is its size, number of rows times number of columns. So I want to multiply a matrix A by a matrix B. Let's say A is an M by N matrix, so it has M rows and N columns. B needs to be N by something. I'll just call that P. So for the product AB to exist, these two numbers in there must be the same, otherwise you can't do it. And the other two numbers tell you the size of the resulting matrix. That's, of course, if the product is possible. So if I multiplied together A and B, the product matrix would be M by P. It would have M rows and P columns. So basically, what this is saying is that in order to be able to multiply matrices together, the number of columns in the first matrix must equal the number of rows in the second matrix. And hopefully, why that is will become clear with my second point. So when you can actually multiply two matrices together, we find each entry in the product matrix, in this case C, one by one. And the entries in C are determined by finding the dot product of a row in A with a column in B. So let's look now at an example with these two matrices A and B. So let's say first I want to calculate the product AB. Well, A is a 2 by 3 matrix, 2 rows, 3 columns. B is a 3 by 2 matrix. So these numbers in the middle are the same, so I can find the product. And then these two outer numbers tell me the size of the resulting matrix. So AB will have size 2 by 2. So let's set up a 2 by 2 matrix. So in the product matrix, which I called C above, so this entry here, this box is element 1, 1. So it is the dot product of row 1 in the first matrix with column 1 in the second matrix. And remember, we've done dot products. We just multiply corresponding elements. So it's 1 times 1 plus 3 by minus 2 plus negative 2 times 0. So let's now go along. This element here is element 1, 2. So the first number was 1. So that's the row from the first matrix. And the second number was 2, so that's the column from the second matrix. So what goes in this second box is row 1 of the first matrix, now by column 2 of the second matrix. So hopefully you're starting to see why the number of columns in the first matrix needs to equal the number of rows in the second. It's so that there are enough elements that line up. So there's 3 elements here and 3 elements here. That's why we needed that to happen. So the dot product of those will be 1 times 9 plus 3 times 6 plus minus 2 times 0. And we keep going like this. This element down here is element 2, 1, so it will be the dot product of row 2 of the first matrix A and column 1 of the second matrix B. And of course, the final element here will be the dot product of row 2 in A with column 2 in B. And now we go through and actually calculate what each of these elements is. And this is our final answer. So this matrix, it's not at all obvious what it will look like just from A and B. So we have to go through this process. So note, if I wanted to multiply B by A, in this case, I could do it. B is a 3 by 2 matrix. A is a 2 by 3 matrix. These numbers are the same, so I could multiply them together, and the resulting matrix would be 3 by 3. And this time, it would be the dot product of each different row in B with each different column in A. But I won't show you how to do that because I think you get the idea. But of course, note AB is a 2 by 2 matrix, but BA is a 3 by 3 matrix. So straight away, that tells us that the order in which I multiply two matrices absolutely does matter. So multiplication of matrices is associative, but in general is not commutative. So let's look at the second part of this statement first. So commutative means the order doesn't matter. So when I say multiplication is not commutative, I mean the order of multiplication does matter. So in general, AB does not equal BA. We saw in the previous example, AB and BA would have completely different sizes. In fact, sometimes AB will be possible, but BA will not be possible, or vice versa. So the order of multiplication generally matters. I say generally because there are a few special cases, special times where the order doesn't matter. For example, we will see later that when we multiply a matrix by its inverse, if it has an inverse, it doesn't matter the order in which you multiply them, you always get the identity matrix. Now, although matrix multiplication is not commutative, multiplication by a scalar is commutative. So C times A is the same as A times C, for example, where C is not a vector but a scalar, just a normal number. So multiplying each element in a matrix by a scalar is the same as multiplying it by C times I. So I is the identity matrix and C is any scalar number. It turns out that when you are multiplying a matrix by a scalar multiple of the identity, it's the same as multiplying each element in the matrix by a scalar. It turns out that in those situations, matrix multiplication is commutative. It doesn't matter whether you put the multiple of the identity matrix first or second, you'll still get the same answer. But these are special cases. In almost all other cases, you will get a different answer if you switch around the order of multiplication. So that's what it means that it's not commutative. So let's look at what associative means. So associative means that when you have a long string of matrices to multiply, it doesn't matter where you put the brackets. So let's say I have something like a squared x. I wanted to use this example because it also involved powers. So when you are squaring a matrix, you're just timesing it by itself. So you can actually only square a square matrix. You can only raise a square matrix to a power. Otherwise, the orders won't work like we looked at before. So a squared times x is a times itself times x. So I can put the brackets here and do that first, or I can put the brackets here, do those first. See, I'm not actually changing the order of the multiplication, I'm just putting brackets wherever I like. And I can do that because multiplication of matrices is associative. So let's look at an example just to convince ourselves of this. So let's look at this example where A is the matrix on screen and X is a vector. It turns out X is actually an eigenvector of A, and we're going to calculate each of these, and we should get the same answer each time because multiplication of matrices is associative. So let's first start with this one here. So A times X, you already know how to do multiplication of matrices and vectors. The rule is still the same. It's the dot product of row in A with the column in X. It's just that X only has one column. So AX will be a 2 by 1 matrix. So the entry that goes here will be the dot product of this row and this column. 1 times 1 plus 2 times 1, which gives 3. And the entry that will go down here, the 2, 1 element, is row 2 in A with column 1 in X. So 3 times 1 plus 0 times 1, which is 3. So if I apply A again to this, so A times AX, which we already found, will be this matrix times our new vector AX. So if we do this, we should get another 2 by 1 matrix. So the entry that goes in the 1, 1 spot will be dot product of row 1 and column 1. 1 times 3 plus 2 times 3, which is 9. And then the next entry will be 3 times 3 plus 0 times 3, which is also 9. So now let's first calculate a squared first and then times it by x. A squared is a 2 by 2 by a 2 by 2 matrix, so the result will be 2 by 2. So the entry that goes here in the 1, 1 spot is row 1, column 1, their dot product. 1 times 1 plus 2 times 3 gives us 7. The entry that goes here, dot product of row 1 and column 2, 1 times 2 plus 2 times 0, and so on. So now we're going to apply this matrix here, A squared, to the original vector x, and we should get the same answer. So again, our answer will be a 2 by 1 matrix. First entry 7 times 1 plus 2 times 1, and then 3 times 1 plus 6 times 1. So we got the same answer here, and that's because matrices are associative under multiplication. So one other point I want to make is that they're also distributive. So if you have the matrices A, B, and C, A outside of B plus C, you can expand the brackets just like you can for normal numbers. That's called the distributive law, and it also holds for matrices. So we say matrix multiplication is distributive over addition. All right, there's just one more point that I need to make. So when you multiply two matrices together, you get another matrix. And that matrix, its columns are linear combinations of the columns of the first matrix in the product, and its rows are linear combinations of the second matrix in the product. So let's first look at the first part of this, linear combinations of the columns of the first one. So I've color-coded the columns of the first matrix, black, blue, and green. We're going to multiply that by another matrix. I just made these 3 by 3 matrices, and we get a matrix here. Its columns color-coded yellow, red, and white. So the yellow column, which is the first column of the product matrix, so it is equal to A times the first column of the first matrix. So here A acts like a scalar, plus the next one, D, next one in that column, times the blue column of A, and then you guessed it, plus G times the third column of A. So that column in yellow is just a linear combination of the columns of the first matrix using here these 3 numbers, entries from the second matrix, as weights. So in a similar way, the red column of the product matrix, it will be, so it's the second column, so now we get the weights from the second column of the second matrix. It will be equal to B times the black column plus E times the blue column plus H times the green column, and so on, and you can probably predict what the last one's going to be. So we can see that each column in the product matrix, which is this one here, it is a linear combination of the columns of the first matrix, and it uses as weights entries from the second matrix there. So that's sort of a quick way you can use for multiplication of matrices, but it's important that we understand that the product matrix, its columns are just linear combinations of the columns of the first matrix. That has really important implications when we're thinking about things like whether or not these columns are linearly independent. So it's a very similar story for the rows of a matrix. Now we're looking at matrices as the amalgamation of some row vectors. So this is the product matrix here. So it has 3 rows. So row 1 is a combination of the rows of the second matrix. The weights come from row 1 of the first matrix, and so on for the other rows too. So it's really important that we understand that. Of course, that means that if you multiply 2 matrices together, the product can't have more linearly independent columns than either of the matrices in the product. So that will have important implications when we look at inverses. All right, this has been the luckiest maths teacher in the world. Have a great day.